Bem-vindos to one more episode of the Type Theory for All podcast. This is your host, Pedro Abreu, and in this episode, we have a terrific conversation with Gerwin Klein. We talk about his work in the formal verification of the microkernel seL4, which was done using Isabelle at NICTA/Data61 in Australia. Gerwin has worked in this project since its conception in 2003 in several roles. He was a researcher, a senior researcher, research group leader, you name it, he has done it all. I will just stop talking here and let you guys draw your own conclusions. So let's get into it. All right, welcome everyone to one more episode of the Type Theory for All podcast. This is your host, Pedro Abreu. And today we will talk with someone who have led one of the greatest endeavors in formal methods, the formalization of seL4, Gerwin Klein. Thanks for being here today, Gerwin.
Thank you for inviting me.
Did I get your surname right? Gerwin Klein?
Klein, yeah, that's
Klein.
Yeah.
Okay, sorry about that.
That's cool.
Well, so we have met around 2015 when I was studying in Australia, and I got to an internship at NICTA at the time. One of the first things that I remember when I got there was that I watched a talk you gave, and you were so passionate about theorem proving. So I must ask, how did you discover this passion? What's your story?
That is interesting. I wonder what talk that was that I gave there. I got into theorem proving not as an undergrad student, actually, just when I started my PhD. But I think I discovered the interest for it during my undergrad. So I had multiple interests that I was pursuing there. So I was really into software engineering and dependable software. So there was one, area where you could see some motivation. I was also really into compilers and generating code. I was actually thinking about doing a PhD in generating user interfaces from specifications and so on. And I guess that was a little bit of the formal specification angle. And then I listened to a lot of lectures from Tobias Nipko, who then later was my PhD supervisor. And there were cool things, like most of them were electives that were not very large. And most of them were in English, which I kind of found cool. And it's not that common at German universities, but there was semantics, lambda calculus, term rewriting, things like that. So fairly deep theory, but in a sense, the way Tobias did them, and which I, as a student, didn't realize at all, is of course because he was doing theorem proving. They were fairly formal, but formal in a way that made sense and that fit together. And he did actual proofs on the blackboard that you could follow, and that were not just random arguments, but actual formal arguments that fit together. And somehow that I found very fascinating. And then one of his PhD students in the semantics lecture, Stefan Berghofer at the time, he actually just went ahead and formalized a bit of the lecture in Isabelle. And that was sort of my first contact with theorem proving. And I found that very cool. Especially all these proofs that we do that could easily be wrong just because I miswrote a letter somewhere on a page. You can check all that. You don't need to get them right. You can do that fully automatically and fully with full assurance, basically. So I found that very appealing. And then, I started a PhD in the area, and that from then I was lost, basically. So as soon as I actually started with Isabelle and proving theorems and so on in the theorem prover, I found that very addictive and very, how should I say, productive and addictive at the same time. It's a very good combination, or very dangerous, depending on how you want to see it. I have a warning in my theorem proving lecture about that.
It's like playing video games, right? You just get so sucked in trying to prove things and make things go through that you just
Absolutely.
can't stop, right?
Yeah, I mean, it's better than the best puzzle games I know. And once
and,
you're done, you actually have, usually something useful
and
as
it's
well.
really hard too, like very harder than the hardest puzzle games out there.
It can be. I mean, sometimes it depends on what you're proving. So if you're
Right.
doing program verification, there's a whole bunch of things that are not actually that hard.
Hmm.
And some proof work I do these days, I do some work that nobody else in the team wants to do, like cleaning up theories and so on, um, just because it's nice and relaxing. And yeah, when it works, it can get very annoying when it doesn't work, but that's
Right.
the case for many things.
So then you went ahead and verified a piece of the JVM. Could you tell us a little more about that?
So I was going to say that was my PhD topic, but that's actually not really right. I'm, I don't know if I should tell the story if all the undergrad students are listening, but
Oh,
I procrastinated a lot. Okay, my real PhD topic, the one I started with, was actually proof carrying code. Um, so that is the idea that if you deliver some code to be executed somewhere, you should also deliver proof that the code does what it's supposed to do. And you could, like, there's different strengths of what you're going to prove about this. Could just be that that it doesn't have any undefined behavior, or that it's safe, or that it does a particular thing, or finishes in a certain time, or whatever. So there was a whole bunch of work around that time that I started my PhD, about 1999, um, in that area. And that was my PhD topic. But I was also on a project, a big European, what's it called? I forgot. European Union something project called veryfing, that had like loads of academic teams and an INRIA team and so on. And the overall goal of that project was to formalize the entire Java language and JVM so that you could write programs about it, write programs in Java, prove things about them, and have all of that assurance go down to the JVM level, basically. Um, the idea behind that was that people were trying to do common criteria certification of Java card, for instance, so smart card applications. And part of that is you need to formalize them. So to push that whole formalization endeavor, there was this huge project, and I was part of that. And my part in it was the JVM and mostly the bytecode verifier in the JVM. So the JVM has this. It's actually it's kind of an interesting machine language. So it's an abstract machine language, a stack language, but machine instructions like, I don't know, load and store and so on. And it has a type system. So each register can have a value of a certain type and so on and so forth. And the bytecode verifier basically checks that the machine program is type correct. And in a sense, that was related to my PhD because types are a form of proof, and type checking is a form of proving things. So I procrastinated almost, I don't know, 2.5 years on that. Wrote a lot of formalizations and actually quite a few papers about it. We formalized pretty much the entire JVM. So a student before me had done most of the JVM formalization work already, which is, what are all the instructions? What is the state of the JVM? What does each instruction do? How does a procedure call work or a method invocation and all of that? And so I completed that, and then I added the type system, and then the algorithm for the bytecode verifier. So there's a type inference thing going on. Then for Java card, there was this idea of, I forget what the industry name for it is. We called it lightweight bytecode verification. It's basically where you provide with the program already a certificate of, like, basically a type annotation. You say for each register what the type is supposed to be. Whereas in a normal JVM invocation, the bytecode verifier is supposed to figure that out by itself. And so if you already have that certificate, then you can do the type check in one linear pass. And the idea, and with no more memory than that, or at least not, with all of one memory over that, basically. Whereas the normal bytecode verifier would need more memory and more time. And that wasn't good for smart cards. So the thing has an industry name, which I forgot. I don't know if they even still do that, but that was quite interesting. And new at the time and so on. So I had a lot of fun doing all that. And I grew increasingly stressed about my actual PhD because I hadn't done anything on that until I, at some point, had a meeting with Tobias about, the state of my PhD and so on. And he basically looked at me and said, "Well, but aren't you just almost finished? I thought this is your PhD now." And that was quite a revelation for me.
It worked out pretty well.
That worked out okay. So sometimes procrastination can be good, but I don't know if I would recommend that path.
So how did it work? Did it have a C implementation and then you also have the proofs in Isabelle, or everything's done in Isabelle and then you can extract something? How did it work?
So I was mostly working from the official Java language specification, which is in natural text.
Right.
There were one or two PhDs before me, like out in the world, not in our group, that had done formalizations of parts of those type systems on pen and paper. So I used some of those to look at how you would formalize these things. But mostly I just wrote the type system in Isabelle, and we were actually, like, the language specification had said which type what is supposed to be, but it didn't specify the algorithm, how you would do that, how you would infer that. And it didn't actually elaborate the type system very much. It just said the bytecode verifier must check that. But it turns out there are some areas of the type system that were actually really complicated. So I remember at some point talking to some guy at a workshop, and turns out he was working at IBM and was implementing part of the bytecode verifier for their JVM. And he said after my talk, "I finally understand what I'm doing here with this instruction." It was a jump subroutine instruction, and I think it was actually removed later. I don't know, like, it's still there in normal Java versions, but I think it was removed for Java Card because it had too many complications. And it was definitely complex to get this right, and the type system looked interesting.
That's a good thing about doing formal verification, because you really had to sit down and really understand what it was doing, right? The other hand, this guy from IBM, he was just like trying to get it over with, and then after you explain, things made more sense for him, right?
Yes, basically, really cool. If you formalize it, you have no chance. You have to do it properly, right? Your proof will not work. When you implement it, you will do it, and if it works, it works so far, and the things that you've tested. But
it seems like it works. So after that, you ended up working in seL4. How did that transition happen? How did you end up there?
So after my PhD, I stayed a little longer at TU Munich. Working a bit more on Java and so on, and finishing up some of the work. But pretty soon after that, like half a year after that, I went to Australia, to NICTA, which was just founded in that year, basically. I think it was officially founded in 2002, and I applied beginning 2003, and then I went to Australia in October 2003. And that was I went to NICTA and partially on purpose into something that was just founded and new, because I liked the idea of the chaos that you get. And which usually means, well, it can be good or bad, but and on the good side, it means there's opportunity doing things that other people either think are not worth doing or think are impossible to do, and so on. And the seL4 verification was one of those. The real idea for it was actually by Gernot Heiser. So he was in a different. So NICTA was organized at the beginning in programs. So I was in the formal methods program. Gernot was leading the RTOS program, which was embedded real time and operating systems. And there was also a logic and computation program in Canberra that Michael Norris was in, who we worked with quite a bit in the seL4 project. And so it was Gernot's idea in the sense that he wanted like high assurance and a high assurance operating system. And I remember that we had this meeting where we were discussing ideas, what the formal methods program should be doing. And yeah, so Gernot was asking, well, can you verify an operating system kernel? And we were not quite so sure. So I knew that there was a project about to start in Germany, the Verysoft project that had a similar goal, or at least there were discussions about it. I think they started about the same time that we started the real seL4 project, because the first thing we did was a small pilot project where we tried out, what bits of OS code can we formalize and verify. We tried out the B tool for formalizing a big part of the current L4 API. There was a whole bunch of thinking of what should that new kernel look like, or should it be a new kernel? There was a whole literature survey session, which was probably in that pilot project, that was the biggest chunk of work. I think it was the literature survey, which was also very interesting. But yeah.
So this was when you guys chose to work with L4, or was that decision made before?
So the RTOS group was a group that was working a lot already with L4.
Okay.
So they had connections to Jochen Liedtke, who is the main author of L4, and like a whole bunch of students were doing microkernel things, and Gernot's been doing microkernels for a long time, basically. So the L4-ish area was kind of clear, but that it would be L4 itself, that was not so clear. We wanted something fast, and it had to be a microkernel because the code size was important, right? Verifying Linux with multi-million lines of code was definitely not in scope. And L4 itself, with about, we were thinking about 10,000 lines we can do. Maybe, there was nothing out there even with 1,000 lines of C code that was formally verified at the C code level. In fact, I didn't know any C programs that were verified at the semantic level that we then built, basically. At least not in theorem provers. And there was some model checking and so on around that time that also was emerging, but not deeper properties like the stuff that we proved. And so there was this 1 year pilot project, and the result of the pilot project was, yeah, we can probably do it. And then we wrote a project proposal and got the project approved, and then we just went ahead and did it. And part of the project proposal was that we were going to write a new kernel, so that it was not going to be L4, but a new kernel version, because L4 had some, how should I say, obvious security problems in the sense, for instance, that if you want to send a message to someone, you just need to know that someone's identifier. So you can that there's no separation as such. You can just guess an address and send a message to them. And that, yeah, we wanted to build a kernel where you can control that kind of stuff, basically. So the whole idea of adding a capability system to a microkernel started there.
So what ended up being the main differences between seL4 and L4 itself?
I think the one main difference is the capability system. So access control in seL4 is very different to L4, and I think the rest is, it's a completely new implementation, but the rest is at least inspired from the L4 legacy. So the idea that you have IPC, which is like a procedure call, basically, that you have notifications and signals, that the kernel takes care of interrupt delivery and acknowledgement and so on. I think those are ideas that already are there in L4, and the idea that it can be fast, and that it needs to be fast to be able to compete with monolithic kernels, basically.
Is it in a similar size as L4, or is L4 much bigger?
I think it's roughly the same order of magnitude. I don't know exactly how many lines of code L4 are. And for seL4, by now, it depends on exactly which configuration you choose and so on. So the one we verified in 2009 is about, like, if you pick the default ARM configuration, the kernel is now about 50% bigger than it was back then. So a lot has changed over time and things added and so on and so forth. But yeah, one of the explicit goals of the project was that it has to be within 10% performance of the fastest kernel that is around, which was an L4 variant. And we actually in the variant we managed to be faster. So
Oh wow,
not 10% slower, but faster
that's
than the
awesome.
fastest kernel that was there. Yeah, that was pretty cool. And I
So
like that was all the systems people basically, right?
I love that. That's really cool. So I'm trying to understand a little bit because okay, so you formally verified your microkernel, which is pretty much your whole OS that you have, but then there is a difference between the code that will run and the code that is being verified, right? And how do you glue those together? So I imagine that the code you're running is actually C code and you're verifying in Isabelle. So how do you do this match in between?
So we actually parse the C code that the compiler sees into Isabelle and reason directly about that. I mean, there's a whole refinement stack on top of that. So security properties and so on are proved about a much more abstract specification. But the main functional correctness proof that we did back in 2009 was the semantics of the C code implements correctly the abstract specification of the kernel. And there was in a layer in between so we call it the design specification or the executable specification that was initially written in Haskell. So there's a whole side angle of this project that sometimes gets confused a bit too much, but we started the entire project by writing a prototype of the kernel in Haskell. And that was good for the formal methods side, i.e. me and my team, because that was easy to formalize and the concepts made sense and we could abstract from that much more nicely than trying to sort of glean all that from messy C code. And it was close enough to something concrete that systems people could work with it. The whole thing worked because back then Haskell was taught in first year, and there was a whole bunch of system students who knew Haskell and were comfortable just writing it and dealing with it and so on. Yeah, so that's how we actually started the project with a prototype, but it doesn't play a big role in the verification anymore. So the Haskell kernel still exists, and we still use it as an intermediate artifact, but there is a completely untrustworthy translation from Haskell. It's just a messy Python script into Isabelle, and that gives you an intermediate specification. And so there's actually two proofs. There is a proof from C to that intermediate specification, and then from the intermediate specification to the abstract specification. And you can put those two theorems together, and then the intermediate specification actually disappears in the final theorem. So if it's correct or not, it doesn't matter for the correctness of the theorem. It just matters for whether you can do the proof or not.
Right, right.
Like if it's wrong, you won't be able to achieve your proof. And
it's like an implementation detail for doing the proof.
Exactly. And there's even things where, like, this is not a proof about the correctness of the Haskell program, because we actually make things up in the translation sometimes. There are commands in Haskell that do nothing in Haskell, but that are, for instance, assertions for our proofs, or that manipulate the machine state that doesn't exist in Haskell but does exist in OSPec and so on. So by now it's a pure proof artifact, but back then in the beginning it was an actual design prototype for the systems people to figure out how do we do this capability system, how do we do it in a way that is fast, and how do user programs interact with the kernel and so on. So Okay, so that's the Haskell side story. Your question was actually about C and the code that runs and the code that we verify. So we try to be extremely close to the code that runs. So that is one of the big things in our project, that we were basically the first larger verification that just took semantics of C directly and verified something about that, basically. So the code that runs is the code that is verified. Later in the project, I think roughly about the time you were visiting, actually, maybe 2014, maybe before. So we did also a binary verification pass. So because if you verify the C program, you still trust the compiler to translate it into machine language that correctly runs the semantics of C, or what we understand the semantics of C is. And so our binary verification pass takes the output of the compiler, so the binary, and gives the semantics to that and compares it to the semantics of the C program of the kernel, and then does a proof that one implements the other. And so that's it's a slightly different kind of proof. That's way more automatic, and there are multiple theorem provers involved. So there's Isabelle on the C side, there is seL4 on the semantics of the machine code and extracting verification conditions from that. And then there's a whole bunch, well, actually by now two, not that many, SMT solvers that get verification problems that are chosen from those verification conditions. So there's a whole bunch of heuristics and so on that are trying to figure out, did an optimization happen? Which piece of code in the source should I compare to which piece of code in the binary, and how big should these chunks be, and so on. So the smaller the chunks, the easier it is to verify. But sometimes if you have optimizations, you need to take bigger chunks and so on. And yeah, that's purely heuristic. And, well, finding is hard. Once you have satisfied all verification conditions, you found the proof. But yeah, so with that additional phase, we're actually verifying the machine code that runs on the machine, not
Gotcha.
just the C code.
Gotcha.
So we're doing that for ARM and for RISC-V, and for ARM for 32-bit and for RISC-V for 64-bit, but not for the other architecture. So how should I say, our minimum requirement for calling it verified, or an seL4 version verified, is to go down to the C. And going to the binary is where we have the tool, basically.
So back then you're already aiming for different architectures?
No, back then we were just aiming for ARM.
Okay.
So in the initial project, we picked one for ARM and did not think much about doing other architectures or genericity or any of that. Like, we were mostly thinking about, is this actually possible? Are we going to make it or
Yeah.
not?
Yeah.
And
I wanna make more questions about that side on how it's growing nowadays, because I think it's related to proofcraft nowadays, right? I'm curious how many people were working at the beginning, and how long did it take for you to finish this formalization of seL4?
so in total, there were 12 people involved, but most of them, or many of them, not actually full time. So I think the full time equivalent, it was 7. And I need to remember, I don't quite remember if that includes the systems team or not. The systems team was not very large, it was a few people only. And yeah, so that's roughly the size. So 7 full time equivalent, and I think about 4 years total. So the original project was, our proposal said 3 years were going to be done, and then we needed another extension of another year, and then we were still not quite done. So there were 3 of us still finishing the last bits of the proof for another few months after that.
So 7 people full time for pretty much 4 years. That is huge. That is a lot of work. what
It's
did you?
yeah,
I
it's
think,
a lot
well,
of work.
for formal methods, I think it's hard to have something on that side. I I don't know. I don't know many projects, but um, how what were the? I imagine it's really hard to, because you had to think of proof engineering, that things that people were not even thinking back then. So you had to kind of create. You guys had to kind of think and create this whole new area of engineering in a sense. What were the challenges there, and what did you guys learn and create for this?
So we did we did create a whole bunch of things. Just on the size, maybe a little bit, because so yes, it is big for an academic group, definitely. Like there are not many academic projects where 7 people work on one specific thing for years. But then again, in terms of projects, like I came as a PhD student, I came out of this Verificard project, and it was at least a factor of 10, maybe 20 bigger than like I mean there were multiple whole research groups funded under that, right? Um, so for it was like I've always had this where the people at NICTA said this is a big project, and I was like, my PhD was in a much bigger project. But like I don't know what you guys are talking about. And if you think of industry, when like companies like Google or Apple or are building products, like 100 million is nothing, right? And this is maybe 2 million in salaries. So you know, there's big and there's big. But okay, it was like for proofs, it was a big project. It was one of the biggest proof projects around. Verisoft was also very big, and we that was running concurrently, and we're actually talking quite a bit, and we even developed some tools together or used each other's tools and so on. So part of the C parser, for instance, the was developed in the Verisoft project, but not for C. That was just more a generic imperative language verification framework, and we specialized it for C and made it into a C semantics and so on. And that project used a more, they called it C0, but it was more a Pascal-like language, basically. So they made their own language to verify their stuff in. Anyway, so there was a whole bunch of things. So one of the things that we did fairly early on was we were since we were 12 people in total, not all of us were working on all of the proof at the same time, but there were times where we had 5, 6, 7, 8 people working in parallel on this artifact. So we built some of that on purpose into the calculate that we were working with. So we had a refinement calculus that we built. There's nothing, I mean, I want to say there's nothing big new about it, but of course there was enough new about it that you could write a bunch of papers that okay, it works this way and it has these properties and so on, and we can verify these things. But how refinement as such is done has been known for quite a while, and there've been books written about it and so on. So the main thing we did is we made the calculus so that you can split up the proof problem so that different people can work on different parts of the proof problem without having to talk to each other too much. As in, I don't know, if you have a function that calls to other functions, what we wanted to achieve is that these two functions can be proved in isolation, as long as you assume the right preconditions. You don't actually have to go back and forth all the time and do it in one file or do it in one proof session even, and all that. So that was pretty successful. Looking back, I think we did a bit too much of it. So refinement has this nice property that if you've proved something on the abstract level, you should be able to reuse it on the concrete level with modulo a refinement relation. And we didn't use that a lot. We preferred, or we did too much reproof of properties that we already had on an abstract level, because mostly it was just easier, and there was no coordination needed, and it was for us probably the faster way to do it the first time. But now looking back in terms of maintenance, it introduced a bunch of duplication that we're slowly getting rid of now, basically. And if you know all the properties that you're going to prove, and know that they're going to be useful, then it is actually faster to just prove them once. But we were at the point we were just trying to figure out what do we even need to prove? What are the invariants of this kernel and so on? And we did not know that we had the right invariants until like 2 days before we finished the entire proof, because you can always at the last minute discover, oh, I need to know this property about this global variable. And if it's a global variable, then it's an invariant about the entire program, because somebody else could change that at some point, right? So that was, how should I say, interesting, suspenseful to the very end. um, but we managed. So calculate was one thing. There was a whole bunch of just little tools that we implemented in Isabelle. So there is this feature in Isabelle now that is called Find Theorems, where you can search for theorems by pattern, not by name or by whatever, by different criteria. Yeah, so one of the people, actually, two, me and Raf, wrote that fairly early on, because reproving things is expensive, and if you do it too much, and if you have 6 people working on it, they keep reinventing all the same stuff. I think we reinvented monads at least 3 times before somebody sat down and made a library, and it's just, everybody use this now. Yeah, that was actually kind of embarrassing, because we wrote a paper about monads, and here's the framework and how does it work, and then I met it was David Basin actually at the conference where we presented it, and said, did you see our paper at ATP about exactly that last year? Damn, I missed that one. It turned out it was not exactly that. So it was,
Okay.
It was good that there were 2 papers, but we did miss his work, and it probably would have helped a bit. I still feel bad about that even 10 years later.
I hate when that happens. It has
Yes.
happened to me too as well. It's like I should have seen this.
It happens every now and then.
Mm-hmm.
So little tools. There's also a tool called Find Consts, where you can. It's a bit like what's it called, Hugel for Haskell, where you find functions by type and so on, and by name. What other things? One cool tool that we wrote back then that unfortunately is kind of broken and has never really worked again was called Levity. So that helps with the thing where you're in a bigger proof, and then you figure out, oh, I need this little lemma about lists that has nothing to do with the proof, apart from I need it here. But you don't want to go back into the list library and add it there, because it's going to take you 2 hours to rebuild everything and be back at the point where you actually need it. So you just put it in the same file next to the lemma where you needed it, and then it is forgotten, nobody sees it, and the next person who needs it will probably reprove it again. So Levity was a tool that built on an idea, I think that was actually somebody in the Verysoft project, where they had the same problem. They did the same things that we did. And they wrote a tool called Gravity that figured out automatically where would this lemma fit, into which theory should I put it. And it would do that by dependency analysis on which constants are used and which theorems are used in the proof. But then it would just make that recommendation and sit there, and that's it. It was just basically saying where would it land if I let it fall. So that's the gravity aspect. And so our tool that we wrote took that dependency analysis, or if the proof engineer had said, fix me, move this too, it would take the comment into account, and then actually take the lemma, remove it from the theory, like cut it out and put it at the end of the other theory, try rerun everything, see if it works, and if yes, commit it to version control. And that was really cool for quite a while. We still have a few theories in the proof that are called Levity Catch, where we wanted the move to not go higher than that, basically. So there were stop points. So we didn't, for instance, want to add things automatically to the Isabelle distribution, to the libraries in there, because you would have to clean them up, and they would have to be a bit nicer, and they would have to pass a threshold on is actually needed to go into into the Isabelle distribution itself. But into our own library, there were no further requirements, so we could just do that bit automatically. The other bit we did sometimes, but manually. Right? So that was a very cool tool. But yeah, by now the interaction model in Isabelle has changed, and it's actually kind of hard to write that tool. We made 2 attempts over the years, but both of them failed. Like one succeeded, and then the next Isabelle version came out and broke the mechanism again and did everything differently. And so we thought, okay, whatever, it's just the dependency analysis is easy enough, and let's move them manually. With the result that we have a lot of fix me, move this comments now in our theories. And every now and again, somebody goes and does move them, but it's not as nice anymore. So we wrote a paper about a bunch of these tools in, when was that? Don't quite remember, 2012 maybe in Kickham. It even wanted, what is Kickham? I should really remember the name of the conference. It was mostly about mathematics and proofs and so on. And I think that was our first real proof engineering paper. And then a bit later, we did other cool proof engineering things. So one of the things that is also very important for Proofcraft at the moment, but it was important for NICTA and the research group as well, is if somebody asks you to do a new proof, how long is that going to take? And how much money do I need? How do you know, right? So especially for the L4 proof in the beginning, I mean, we estimated it's going to take us 3 years. We're going to need that many people. And well, we needed a year longer and with that many people. And even that didn't, like, the additional year almost worked out. It was, a little bit more in the end, but not significant. I mean, okay, that was at the time a very high risk research project in the sense that, I mean, there were actually people telling us, what are you doing? This is impossible. Basically, the scale doesn't work, the level of detail doesn't work, and nobody has done this before. Why are you wasting your time? While we were, doing it. So the question was estimation. How do I figure out how much time a proof is going to take? And one should understand upfront that this is an impossible question to answer. Right? There's not going to be an algorithm that is going to give you a reliable answer for this. Like if you think of I don't know, let's say Fermat's last theorem. A few person hours in that, a few hundred years. And it looks tiny and small and very, very innocent. So you're not going to look at a mathematical theorem and say, this is going to take me 3.7 years and 2 people. That's not going to happen. But if you do program verification, where most of the things are boring, and you have done maybe a similar one before, there should be something that should at least give you a hint, right? Like, is it going to be 10 years or is it going to be 1 year? And so we paired up with the empirical software engineering group in Data 61. No, it was actually still NICTA at the time. And that was a group that did, well, empirical measurements in normal software engineering. So in particular, Ross Jeffrey was one of the people there who had done many studies about estimation, about how long things take, about productivity, how many lines of code does a programmer write in these circumstances, in those circumstances, and so on. And so we were looking at the data we had about alpha verified and some of the projects that came afterwards, and we're trying to see how much we can extract from that. So one of the things we found fairly early, in fact, that was in the extension proposal, where I had to write a justification. Why are we not done yet, and why do you want more money? So I tried to figure out why we misestimated that, and the reason I came up with, and I still think is the correct reason, is that we were thinking of the effort of this as linear. Like we did a little bit of verification in the pilot project, and we basically thought, okay, the kernel is going to be that much bigger, and let's take a fudge factor for safety, and let's multiply. And that is the wrong thing to do, because if you're doing invariant proofs, your effort is going to be quadratic, at least in the size of the program. It's not going to be linear in the size of the program. So that's, in fact, if you think about it, that's why modularity is extremely important, because modularity allows you to keep invariant small. So if you have to prove an invariant about a module, then you prove it just about the module. And yes, it's quadratic in the size of the module. But if you have another module, you have another invariant about that, it's just going to be quadratic in the size of that module and not in the size of the sum of the two, which would be much bigger. And in a microkernel, there's not much you can do in terms of modules. Like the whole philosophy is that if it can be taken out of the kernel, it should be taken out of the kernel, should be done at user space. So if there's something that is nicely modular that you could remove from the other set, you would probably put it into user level. There's a little bit of modularity in how you can organize it and so on, but not in the sense that you would have in, I don't know, like Java packages or actual modules in a programming language. So that was one thing we found out. And later we looked at a bunch of data that we got out of, I don't know, adding a new feature, for instance. How many lines of proof did that give us? How long did it take us? And we did actually get a quadratic. So the quadratic line was the best fit of the ones that we tried for that data. And we also used the archive of formal proofs and took a few sessions that looked like program verification, and they behaved mostly quadratically. So that was one interesting find in that. What else did we do? We looked at the relationship between time and lines of proof. So lines of code is is in a way is a singularly stupid measure, but it actually kind of works. Like if you don't apply it to an individual, if you apply it to a team that is not trying to game it, like it's very easily gamed, of course. But if you're not trying to game it, your effort is going to be roughly proportional to the lines of code that you write. And it's the same for proofs. Your effort is going to be roughly, the time you spend on it is going to be roughly proportional to the lines of proof you write. Of course, you can game it. And of course, there are people who write way more lines of proof in one day than other people. And that might be either because they're actually producing more or because they have a much more verbose style. But if we take the average over the project, we found all of that doesn't really matter. Like it all goes down in the noise, basically. If you take the entire team and look at it over time, and then we really, that was probably one of the hardest or most effort intensive things we did for these empirical projects is we looked not just at the version control for how much time it took people, but we write progress reports in our group. So this week I did roughly, I don't know, bullet points, these things. And so we went through all the progress reports of the entire team for the entire, I don't know, 5, 6, 7 years by the time we did that project, trying to figure out how long did the team take for this feature or that feature, and annotated these with data points and so on. And so what we found there is that yes, it's pretty much straight on proportional. There's still problems where the problem is small and 10 lines of proof took you 2 months, because maybe you write 1,000 first and then you realized actually it's much better to do it this other way, and then it's small. That's like with code. Like none of this means those don't exist. It just means in high numbers those are rare. Basically, you're not going to prove Fermat's theorem every day. You're going to prove boring things every day, or not boring things, but they might be interesting, but not. In terms of size, roughly proportional to to what you write. So the amount of thinking you do per line of code is basically is the same. And some of it, like for some people, there was at least a hypothesis that we're actually constrained by the typing speed. Like we could be faster if we could write the same proof in fewer lines of code. So that led us to the Eisbach method language. So that is in Isabelle, you can write new proof tactics in ML, and that's always been there, and it's part of the LCF architecture. So it's not soundness critical. You can just go and write a bunch of ML code and automate certain proof steps. We tended not to do that a lot. We have written a few, of course, but not small casual ones. Not here are 10 proofs that I did where I found repetition after the third one, and I don't want to retype everything every time. I want to write a short tactic. That sort of casual, let's write a short tactic didn't happen because going to the trouble of writing this in ML is kind of, you need to know ML, you need to stop your proof, think on a different level, write a whole bunch of boilerplate code, and so on. So we thought, okay, what if there was a method language where you can make a method definition in the same language that I do use in tactic proofs, basically. If I say, I don't know, simp add something, comma, fast force, comma, auto, or whatever in my proof, why can I not say that as a method definition? And so there was one PhD student, Dan Matichuk, who took that on. And that was very successful. And I think he was in the podcast as well, actually.
He was, yeah. We talked about that. It was very fun.
So that was a very, very cool PhD, I think. And yeah, so we're using that quite a bit now. And I don't know if it has, increased productivity in huge amounts, but I think it has increased productivity in the sense that at least it feels better. Like it's very frustrating when you're introducing repetition yourself, right? A lot of engineering is like in software engineering as well as proof engineering is removing duplication, and it's good for multiple dimensions. Basically, duplication is bad for maintenance, and like if something changes, now you have to change it 5 times. If you've removed the duplication, you only change it once. If it's good for performance usually, because if you improve it once, you improve it everywhere. It's what was the other dimension I was thinking of? I just said it. Basically it comes all down to you can spend your effort once and you can spend more effort on that one time than you would do if you just repeated it everywhere. And it's much more agile as well. So changing it once will, is easy. Changing it 10 times, you really think about doing that. Like there's still, I don't know, renaming a theorem is an expensive operation because just search and replace. Well, sometimes it works, and you can figure that out. But there is no rename theorem refactor in Isabelle JEdit or something like that, and it would be hard to do because the scope is. You'd have to make sure that everything where you want to rename it is in scope. But if it's just a string, then, well, if the name is the same as the name of a constant or as a type or whatever, then you can't just go search and replace. You have to do this a little bit more manually. You can, lemma names are not so bad because you can usually figure out the context fairly easily. Renaming a constant can be super annoying. So there's this one thing where, at one point, what was that? We had synchronous and asynchronous IPC. And at one point, the systems team, well, specifically Gernot, was getting really annoyed with the name async IPC because it's not really an IPC. It's just a notification. So I wanted to rename this to notification. It's renamed everywhere in the code now. And that probably took at least a week of work doing that in the proof because, somebody needs to go through all that and figure out which bits are the name in the code and which bits are in lemmas and so on. And I think there are still mentions of async endpoint and async something in the proof base somewhere.
Right.
Because they're hard to find, and if you find them, you can't just do it locally. It's a global operation, and then
Right.
running the proof for one architecture from start to finish is about 5 to 6 hours on a fast machine. So you don't do that just casually. You just you do it when it's really worth it.
Mm-hmm.
So some of these technology could help it, but yeah.
You really have
So
to
don't
think very well what you're gonna name your things because they're very expensive to change later.
exactly naming discussions are heated sometimes. And I mean, there it's painful when you haven't done it in the beginning. So like in the first project, we had none of these concerns, right? Um, when we wrote the library, for instance, for monads, we just wrote what we needed at the time, and we let it grow organically. We tried a little bit, the basic operations. They all have their weakest precondition lemmas and what's on. But if somebody needed a new monad operation, they just added it. There was no big discussion about what it should be called or what scope or whatever. We just did all that. And some of that is still there because it's so hard to change. Now, when we add something, we're a lot more careful and a lot more thought goes into the seemingly trivial things. And I think that's really just a shift between research and trying to do something for the first time and engineering where you're going to live with this for another 10 years and your decisions now are going to hurt you later. Like back in the beginning, we had proof engineering problems like levity and so on, but we did not think about, okay, the next 15 years are going to also be about this, right? We were just trying to achieve it once. And then
You didn't even know if you could achieve it once, right? Then.
exactly, yes.
So there were also other projects that kind of gravitated around seL4. I remember there was the file system project, Cogent.
Hmm.
What were the projects happening there, and what did you guys were trying to achieve then?
So I think Cogent and file system verification was probably the biggest other verification project that we had around. We had like doing Icebach, for instance, was a separate project as such, and all the proof engineering, the empirical stuff was a separate project. What else did we do? So a lot of things were around seL4. So for instance, the binary verification, also a separate project. We did proofs about access control.
Binary verification of what? Sorry.
So the idea was binary verification of seL4. It's really translation validation of the compiler. So that last step
gotcha.
between C and executable. So that was a PhD thesis, basically. Yeah, and in later stages, then more engineering and more people on it. But the initial project was a PhD thesis by Tom Sewell, who is now at Cambridge, I think. Yes. Other projects: access control, information flow, using seL4 as a separation kernel, doing hypervising with seL4. Those were all projects in that area. We also had a little real-time OS called Ikronos that we did verification work on. The verification there was a little bit different to seL4 because we were, on the one hand, interested in a extremely preemptible kernel. So seL4 switches off interrupts when it starts and switches them back on when it finishes. So it's not preemptible in the kernel. Just user level is preemptible. And Ikronos was something for small microcontrollers where you have a few cycles to respond to an interrupt and so on. So you can't afford to switch off interrupts when you're in the kernel and then switch them back on. You have to handle it immediately, basically. So we were interested in that concurrency aspect. And then we also wanted to verify absence of undefined behavior. And for absence of undefined behavior, we went with model checking with CBMC back in the day, and that worked pretty nicely. It was also because the code was written to be extremely static, basically. There were no loops over dynamic data or anything like that. Like all data structures had a pre-configured length, and the only for loops were over that. There was one loop that was potentially non-terminating, where we told the model checker to, shut up and not care about it, which is the typical spin lock thing, where you wait for the other process to do something. And well, you don't know that that loop is going to terminate. You only know, well, if you know both processes are doing something, you do know. But even then, it's actually very hard to prove, because the semantics of the processor is not necessarily that you see the effect immediately. You will see it at some point later, and in reality, that's maybe 2-3 cycles later. But in a formal semantics, how do you phrase that? Usually, you would say will arrive eventually, and that means not necessarily. Well, actually, it does mean termination. Well, we just hand waved that basically. We said that informally. Like if the bit is going to be set eventually, then that means this loop will terminate eventually. But yeah. So that's the kind of verification we did there. It was a bit different to seL4, but it was a fun project. Yeah, I think that's roughly about it. And what came out of, there's a whole bunch more that we did later. The whole KML area. So KML is a project that is not from NICTA or Data 61. It's I guess Magnus Marin's group. So in Sweden. So his work is all the in Hall 4 is all the reasoning about binary code stuff that we used for binary verification, and so that's how that collaboration started. And another big project that he had is this language KML with basically an ML dialect with a fully verified compiler. And so we're looking at using that for user code on top of seL4, because one of the more bigger research questions was, okay, we verified seL4. How do we get more verification to bigger things? We can't manually verify everything all the time and see that that's not productive enough. So if we could write stuff in ML, verifying things about ML programs is much easier than verifying things about C programs. So we looked into using KML. We actually use it for the system initializer on top of seL4. So when seL4 boots, it hands off to a user level init task, basically, like in Linux, there's an init boot task, and that init task has authority to everything. It has all authority to all the hardware resources that are there, all the interrupts, all the memory, everything that's there. And its job is usually to load and boot up all the other components in the system, give them only limited authority just to the things they need, and then remove its own authority and go to sleep. And so that is a program, it's a user level program that we verified. We verified it only on the model level in Isabelle. So we wrote down what it should do in Isabelle, and then we implemented it in C, but we didn't prove the connection like we did in seL4. And then at a later point, we looked at from the Isabelle definition, can we get automatically a KML definition of that initializer? And I think we ended up doing it a little bit differently, doing a more manual KML implementation, and then an automatic proof that it does the same thing that the Isabelle formalization does. But the effect is the same in the end, that we have a verified system initializer kind of thing. The downside with the verified initializer is it doesn't have as many features as the C initializer, so people still keep using the C initializer. But yeah, that's always a problem.
But then the C initializer is not fully verified, just the KML one. Mm-hmm.
Yeah. Mm-hmm. So the idea is if you're just casually developing on seL4, you probably want to use the C initializer because it's quick and easy to do and to use. And then if you want a high assurance system, you replace it with the KML initializer. And depending on what kind of system it is, you might still need to extend it with some features that you need. That's one of the things Proofcraft can do, for instance. In general, if there's something with seL4 that needs further proofs, we would be one of the people who you can go to and say, do this for me for money, and we will usually do it.
I should have probably asked this a little earlier, but what exactly does it mean that the seL4 was formally verified? What is the main theorem, and what are the assumptions behind it?
Okay. There are now many more theorems than there were back then. So I'll go functional correctness first. So that was the theorem in 2009, and still the main central theorem that we prove, and that is sort of the threshold for calling a version or feature combination of seL4 verified. Okay, what does it mean? The theorem is that the semantics of the C code correctly implements the abstract specification of seL4. And the abstract specification is, you can think of it as a monadic functional program written in Isabelle about abstract data structures. So it has, it uses sets and Isabelle lists and so on for things, but it also talks about the binary interface of the kernel. So it describes, if I make a syscall to seL4, then I'm, handing parameters in these registers. And if I put these values in and put these other values in these memory locations, seL4 will respond in that register with that number and will change its internal authority state and so on in this way. That's roughly what that specification says. So the theorem is just the kernel does that. The C code, the semantics of the C code does that and does nothing else. So that's actually the more important part. If you like, what people usually want to hear is it does that, but what's more important is it does nothing else than that. So for security and safety, you usually want, there's no other behavior. It doesn't do any random stuff, and also sparks memory all over I don't know, devices or something. So that is part of that theorem. What that implies is for the C code is that there's no undefined behavior, because undefined behavior means you don't know what the machine is going to do, and we always do know. There are no things like null pointer dereference and all the buffer overflows and all the things that basically are undefined behavior in the end. So yeah, that's what the theorem says. Assumptions. Let me think a bit. So the main assumption is from which the rest basically derives itself, is that the machine correctly implements the semantics of the C code that we give it. And so the question is, what does that mean? So for instance, this means that there are a bunch of assembly instructions in the kernel. So there's inline assembly and like the trap code that does actually enter the kernel and so on. Those are assembly instructions, and we have a formal model of what they do, but we have no proof that those assembly instructions actually do what we model, because they're not really part of the C semantics as such. So those are a fairly big assumption. Well, fairly big compared to non-verified code. It's super tiny. It's like almost nothing, and you can look at it manually and actually read the 10 lines or whatever of assembly for each of the bits. What others? Caches and TLB. They're also behind this so-called machine interface for us. We have actually had a PhD thesis about how to model the TLB, and also a bit on how you would integrate that into the seL4 proof, but we haven't done that yet. Like, it's not integrated into the big proofs. But we do know how to formalize it, basically. Caches we have not, and there's actually, every now and then, if there's a new platform and people port it by just copying and pasting code, there can be caching bugs, in the sense that this can be correctness relevant. It's usually not correctness relevant for the kernel, like it will not kill itself, basically, or run into undefined behavior, but it might lead to things that you don't want for the user. So a typical caching bug bug could be that a user can read things that they're not supposed to read because they're not flushed from the cache, even though you thought you flushed the cache. Stuff like that. So that is an assumption you actually have to, validate if you want to do a high assurance system. There's a whole bunch of platforms for which they are validated, but new platforms come in all the time. What else? TLD caches, machine code. And well, okay, the big assumption that the compiler implements the C semantics in the way that we think it should, that is there for the platforms where we don't do binary validation, basically. So where we do binary validation, the assumption is that the machine executes the machine code according to the semantics that is given. And if that's also not necessarily given at all points. So things like meltdown, for instance, where, how did that go again? It's been a while. It's basically where you could read and I think also write to memory that you don't have access to, or where the page table would say you don't have access to via speculative execution. And I think it was mostly just reading, but I might be wrong. So you will get an exception from the machine eventually, but you will have read the memory and you will have gotten the information. And well, our machine semantics doesn't have anything like that. It says, you will read what you're allowed to read, and you will not get access to the things you're not allowed to get access to, according to the page tables. So if your machine doesn't behave that way, then well, the formal model doesn't quite predict what the machine does. All these, spectra, meltdown, and so on, they're important for information flow. They're not so important for the kernel functioning correctly. Well, depends on what you mean by correctly. So the behavior of the kernel is right, but you might still be able to infer information that you're not supposed to infer. So I guess it's mostly the information flow theorem that these are a threat to. But they're there. And one that I like to point to is that a lot of these assumptions they sound formal and formalistic and so on, but they can be very real in the sense that you need to operate the equipment in the right operating environment. Like if you have a mobile phone with, let's say, I don't know, your verified kernel and so on, and you overheat it and put it under radiation, the theorem is off. Like the predictions of the theorem will not hold because the hardware does not satisfy the hardware assumptions anymore. And there's nothing you can do with proofs about this, right? There may be countermeasures, but these are not proof countermeasures. Or if you drop your phone into a volcano, it is not going to, satisfy the refinement theorem.
It seems to me that a lot of the assumptions that you guys had to work with has to do with, how C works and how it can be a little bit undefined sometimes. Do you think that
yeah.
if you had a more well-defined language, like with more well-defined semantics, such as, I don't know, maybe Rust, do you think it would have better verification, or would be easier to make your verification?
So I really like Rust, but I don't think so. So the thing is, why I said when you said more defined language and so on, we to put it provocatively, we don't really care about the C standard at all. Like, yes, we do care a little bit because the C standard tends to be what the compilers do, but what we actually care about is what the compiler does. And so if we use two compilers, GCC and Clang, and from time to time we do actually use ComCert, but it's not in the regression tested at the moment, and as usual, when you don't test something for a few years, it'll stop working. But it was for a while, and it works just fine. It's just GCC and Clang produce faster code, and with the binary verification that we have verified faster code. The things that are undefined behavior in C are things that we need to avoid, and we do know fairly precisely what we want to avoid, and we know that pretty much simply by over approximation. As in, we demand stronger things from C programmers than what the C standard would demand. In that sense, our subset of C is a more defined language already. It is a bit funny because our subset of C does have things that, according to the standard, strictly speaking, are absolutely undefined behavior. Because you can't implement malloc in C without undefined behavior, because the standard says your memory has to come out of malloc. So if you don't have malloc yet and you have to implement it, you got to do something. So and we have to implement malloc for the kernel and then later malloc for the user and so on and so forth. So we have to do some things that are strictly speaking not okay, but we keep them to a minimum, and we know that the compiler does the right thing for them because we look at the binary. Yeah, and that's pretty much it. Compared to all the normal stuff that is undefined behavior, we definitely exclude that in the parser already. Like even, like for instance, you have this thing in C where the evaluation order in expressions it's not undefined, it's implementation defined, so it's up to the compiler. If I have f of a plus f plus g of b, for instance, it could first evaluate g and then f, or first f and then g. And if they have no global side effects, it doesn't matter. But if they do, and they interact with each other, then it does, maybe. And so we just forbid that. And the parser will check it. It will try to prove that they have no side effects. And if that's successful, it's fine. And if it doesn't, it'll complain and say, make this two separate expressions. And then, you have a defined execution on. And normal C programmers would probably hate us, but that's what we demand, basically.
Gotcha. Yeah. So you deal with that.
Yeah. There are also features like taking the address of a stack variable, for instance, that we don't allow. That's not implementation defined or anything. That's just annoying to formalize. And it's something we're thinking about dropping, because working around that can be a bit annoying. In seL4, it was not too big of a deal, but if you want to do user level verification, then yes. And there are a bunch of groups that are using our tools for doing user level verification, I think. Yeah, I think it is, yes, it is public that Apple does firmware verification and user level code verification. And they're using some of our tools for that. So we're, talking to them from time to time and what they want and need. And they're actually basically contributing some of their code and so on sometimes to add more features to that verification. But so I think what my point is that that C subset can be annoying, but it is on a level where it's realistic, where you can write real code with it.
Gotcha. Good.
And you can make it less annoying, which is where the Apple direction is going, I think.
Cool.
Because, yeah.
Okay, so let's put aside a little bit the technicalities a little bit, and I would like to understand a little more about the organization side behind seL4 and everything that you have been working on. You mentioned that you finished your PhD and you went working on NICTA, and then it became Data 621 at the time. So what is NICTA? Where does the money come from? What is the organization behind the interest in this sort of work?
Okay, so NICTA unfortunately doesn't exist anymore, but at the time it existed. It was a national research institute in Australia. So it had a pretty good level of base funding, basically, where it's just a funded research institute can hire people and do its own research projects. It had a mandate to work in certain areas, and it got reviewed every year and so on and so forth. So it couldn't just do whatever it wanted. It had to do things that were in the national interest and that the sort of I forget how they're called. They're sort of national research priorities that come down from I think the government, basically. I'm trying to remember who exactly is involved in setting them, but I think that is mostly the government, and different parts of government play into that. But cybersecurity has been one for a very long time, for instance. So NICTA has base level funding and then third party funding, like other research institutes as well, like grants and so on. It was actually fairly difficult to get grants in Australia because we were not eligible to get funding from the typical Australian grant institutions like the ARC that universities would get funding for. Because the reasoning was because NICTA is already getting government funding. So it shouldn't get, again, it shouldn't compete with universities for the rest of the government funding. It should get other funding. So government funding from Australia was hard for us, but we were fairly successful with like DARPA funding, for instance, in the US and so on.
That's funny because you're getting money from the US, but not from Australia.
Yeah, exactly. It's always been kind of funny like that. We also worked a whole bunch with the US Air Force and US Army, think also, yeah, and with some other US companies. So in fact, most of our funding was from the US, the third party funding. It was at some point bigger than the base funding that we had, but we always had a pretty good level of base funding. So seL4 itself, the first project, was entirely base funding. That was mostly, and internally how that works is, well, you write a project proposal to, for X many people in the research institute to work on that project or to hire new ones. And you get a budget for that if it is approved. The approval process was, I guess rigorous is the right word. It wasn't easy to get to get a project running. Easier in the very beginning, and then increasingly more bureaucratic, and then in fact towards the time where they started to shut NICTA down, we had a really good process going actually. But that's politics. Yeah, so that's how the initial level of funding worked. And a lot of that is how groups. So there were three main programs involved in NICTA, and a lot of that depends on how much of their base funding do they want to contribute to a program like that, right? Or to a project like that. So we found enough people who were interested in that and thought it was possible and a good idea to do, and that was one of the big steps. And then writing a good proposal and getting it funded was the other one.
So if I understand, what about your relationship with UNSW? In order for you to be hired by NICTA, you also have to be a professor there? How did that work?
You do not have to be. In fact, it's kind of the other way around. If you were a NICTA researcher, there was usually the option, if you qualify and so on, to also become a UNSW conjoint lecturer or professor or whatever, depending on your experience and rank and so on. And so that's how it worked for me and most of the full-time researchers that were in NICTA. But there were also people that worked just at UNSW and then collaborated with NICTA. And it could be just collaboration, and there were just, UNSW people who collaborated. There were a whole bunch of them actually in the seL4 project as well. It could also be that part of their salary is actually paid by NICTA, and for that maybe they get teaching relief and so on. There were a whole bunch of constructs. That does not happen so much anymore. Well, NICTA is not there anymore. It got so at some point the government, specifically Tony Abbott, if you want to know the Prime Minister of shame, decided NICTA didn't generate enough money to support itself and still needs government funding, and that's not what they wanted. So they basically said they wanted to shut it down. And then there were a whole bunch of ideas of, what should we do? Should we just shut it down and be done with it? Or what other options are there? And one of the options was to merge with CSIRO, which is the main applied research organization in Australia. And it's very broad. It does everything from astronomy and marine biology to, I don't know, agriculture and what else. It also does some computer science. And so that is how Data 61 was founded. So the computer science part of CSIRO merged with NICTA, and that is Data 61. And Data 61 basically still was just a department of CSIRO. It's not its own organization as such. It had a CEO for a while. I think by now they're not called CEO anymore. They're directors, and it's really just a part of CSIRO. Yeah, that was that. Data 61 as such still exists. I don't think there is much NICTA people left over in there. They had a fair bit of turnover after the merge and so on. It is very different working in a small research organization that has some government funding compared to an actual government organization that is very big and does not do computer science as its main thing. Like if you have to fight against the perception that computers are there to type texts or do statistics, then it's not the greatest environment for doing computer science research. Not that there isn't any. It's just it's different if you have a dedicated organization, right? And then at some point, Data 61 decided that the research direction for computer science now is AI, and everything that's not AI is basically will be shut down. And which is kind of, so we were part of that. By the time we were called the Trustworthy Systems Group. The funny thing is that, of course, formal methods has always been part of AI. Like it's one of the founding things of AI, but they mean the machine learning AI. They didn't mean the formal methods AI. And fine. So in the end, I'm kind of very happy with that. But it was a very turbulent time for a while because, like with NICTA, the question was, okay, what are the options? What are we going to do? And we basically kept the Trustworthy Systems group alive by moving most of it to UNSW. And there is a Trustworthy Systems group at UNSW right now. There was a very, how should I say, visionary head of school back then who just said, I'm going to fund the entire group for half a year until you can find external funding. And by now, so Gernot is leading that group. And by now he has found way enough funding. He's expanding again, basically. That was never one of our problems. We always had fairly large amount of external funding. I think we were one of the best externally funded groups in Data 61. So purely political, we want to do AI kind of decision, not a performance, or at least as far as we can tell, kind of decision. At roughly the same time, actually, before the whole, we're going to shut down OS and formal methods research, me and a bunch of colleagues had started to think about doing a company in that space, because one of the things we were seeing was that more and more commercial companies are getting into formal verification, need formal verification services. People want to use seL4, but I don't know, let's say it's verified for this and that ARM platform, but they want to run a different ARM platform. As a research institute, it's yes, you can make that contract and get external funding for it, but it's just going to distract you from what you actually want to do, which is research, right? So we founded that company to basically serve that area. So if somebody needs formal verification services around seL4, that is exactly what Procraft does. We also do consulting and training around that area where, in the extreme case, it could be, I want to build up my own verification group and verify stuff, and we could help you with that. I would still recommend hiring at least one formal verification person from that already knows and is an expert in the area if you want to start with that. But we can still help in expanding that and figuring out what to do first and so on.
When was it founded?
2021.
Okay.
So in the actual founding date is April 2021, but like May 1st is basically what we have on our website. So we founded it immediately after that shutdown thing. So when that shutdown, like we were thinking about it before, but we were actually going to hold off for another year or so to make a smoother transition for the team, because we didn't want to damage the research side of it. And that's now all on Data 61. They damaged the research side of it. Because I mean, what happens in these situations, right? I mean, the people working in our group, they were extremely highly employable, in the sense that some of them had a new job 3 days after the news was out.
Wow.
Like I had some people call me like from bigger industry, like I don't know, 3 months later, and asking, hey, we heard that the research group closed down, and are there any people who would be interested? And it's like, they're all long gone.
You were too late.
Like, way too late. And yeah, and they went to all kinds of places too. I don't know. Some work for Apple now, Microsoft, and Google. Some work for small startups. Some work for I don't know, automotive, and so on. So in a way, it's kind of cool because now we know people everywhere.
Yeah.
But it would have been cooler to keep them together and push seL4 a bit more strongly. So in 2021, development around seL4 was a bit slow, but it's picked up quite a bit again. We also had the seL4 Foundation just started at around that point, and that has also been a very good thing in the sense that companies and so on that are interested in that can join the foundation, can pitch in some funding to, for the ongoing maintenance and support and so on of seL4. So that actually all worked out pretty nice, I would say. So now there is the research group that still does research around it. There is the company for the verification part. There's a whole bunch of companies that are doing systemy things around seL4. Like, I don't know, Cry10, for instance, is one that is building an operating system around seL4. And there is the seL4 Foundation that has sort of the governance of the entire project. So it determines where seL4 is going and what procedures there are, how do you what do you need to satisfy to accept a patch and stuff like that. Where there's two bodies. One is the technical steering committee that I'm the chair of, that does all the technical bit, and then there is the board of the foundation that does the financial bit. That says, what do we want to spend money on? And they're fairly separate in the sense that the technical steering committee determines the technical direction and content without, there's no company influence. Like if a company pitches in a lot of money, they get a seat on the board, but they don't automatically get a seat on the technical steering committee. That's by, how much experience do you have with seL4 and so on. So that's worked out pretty well so far. So in the end, I'm actually kind of really happy that happened. At the time, I was not so happy. It's yeah.
Sometimes
it's what you make of
bad
it.
things comes for the best in the end and
Yeah,
takes
exactly.
you to very good places. So who are your main clients for Proofcraft right now?
So I can't talk about all of them, but we do a lot of work for the seL4 Foundation. So some of the money that the board can allocate, for instance, goes to Proofcraft for, I don't know, a funny one that you might not think is, for instance, doing all the continuous integration test infrastructure. That is something I did learn like via Proofcraft for the foundation, but also proof projects, things that are not likely to get big funding from other areas. The foundation will fund, like, I don't know, making the proofs better or faster in some aspect, or adding a feature that will benefit everybody but nobody wants to pay for, and things like that. So that's one direction. Another are I think the biggest one actually are research funding organizations like so we currently have a project with NCSC in the UK. So then Cybersecurity Center in the UK was part of GCHQ. Turns out they've been interested in seL4 for a very long time, and they pitched in with quite a bit of funding for a whole bunch of projects. So we're doing that mostly together with UNSW, and that is more researchy kind of work. That's kind of actually it's the work we like best. It's research. It's good for seL4, and it's funded, and it's for somebody who actually wants it. It's not just research funding because hey, it sounds like a good idea, but it's research funding because we want this feature. It's gonna help us. I don't know, do something, build something, or well, I don't know exactly what NCSE wants to do with it, but
it must be a really good feeling. It must be a really good feeling to look back and be in that position that you didn't even know if this project was going anywhere, and nowadays people are actually using it and paying a lot of money to move it forward, right?
Yeah, that is pretty cool. And yeah.
That's nice. So are you still teaching at UNSW?
Yes. So I still have my conjoint professor position. It's the conjoint is actually kind of a strange construct because it's a NICTA artifact. It's usually a title that comes only with in medicine with teaching hospitals and stuff like that. So that you have that in computer science is a bit of an anomaly anyway. So I'm not sure what will happen when that runs out. Probably it'll turn into a normal adjunct professor or something like that. But I still teach. I'm planning to keep that up. There aren't that many theorem proving courses around in the world, and
yeah,
it's fun to teach. And I don't teach it alone. So we're actually right now with 4 lecturers, which means there's not a lot of effort for each of us. Again, and everybody has their section of the lecture that they've done before, so it's not a huge time commitment compared to the fun you have.
Yeah. How big are the classes usually?
It depends. In a very small year, it could be just, I don't know, 5, 6. In a big year, it could be, I don't know, 35. Enrollment at the beginning is usually higher, like could be 50 or 60, but some of these never turn up. I think that's just overcommitting for being afraid of not getting a place. So it's some years when there are really loads of students, there are courses that are just full and you can't take, and and then people apply for more so that they can have a fallback basically.
Is it part of their main track, or is it?
It's an elective, so you don't have to take it. Yeah.
So yeah, it must be.
Yeah. You go.
You're gonna say.
It's fun teaching. It's we had an accident once where the prerequisites were not in sync. So it's probably, I don't know, probably 10 years back or so, where the university introduced a new degree. Or was it Masters in Information Technology, MIT? And suddenly I had MIT students in my course, and I was like, what is this? Surely they're not MIT students. And since it's a master's program, master's in Australia is more I have a degree in a different area, and I want to learn about computer science. So what I had was, for instance, accounting students who could take that course because there were no prerequisites that would preclude that, and I don't know.
They never programmed their lives.
And they probably had programmed, but they had never seen logic or functional programming or any of these things before. And I am very proud that I managed to pass almost all of them. So
nice.
That was pretty good. I mean, they're also obviously interested. I mean, you can drop the course at any time in the first few weeks without penalty. So it's those that stayed were interested or needed the credit. I don't know.
How's the What usually do you teach them, and how are the do they have to do any projects?
They have to do 3 assignments and an exam, and the assignments are multi-week, so they're little projects basically. The first one is not it's not so much a project; it's just a bunch of proofs and a bit of lambda calculus and so on, and sort of what I call the assembly level of proofs, where you apply single rules and say, I don't know, all introduction and conjunction elimination and so on, just to learn about what the logic is like and how things work under the hood. Um, the second one is usually about functional programming and recursive definitions and induction and data types. So there you can do little projects already. Like, I don't know, implement a an interval list, for instance. So implement a set with a list of intervals instead of just enumerating everything, and then have an add and a remove operation and prove theorems that they're correct and so on and so forth. Yeah, things like that, or about trees, or about, I don't know. We try to do a new one every year because they tend to leak, and people put their homework on GitHub these days, and I don't know. We had at one point, that was really funny actually. We had at one point a student who was trying to get answers to the assignments from one of these, paid homework services, and the only
Right.
reply was, "We don't have anyone who knows how to do this."
That's so funny.
That was pretty funny. And the third assignment is usually something about C verification. So the course builds up about from complete basics to I can verify a little program in C.
Wow, that's really cool. That's really cool.
That's, yeah. Yeah, people seem to like it. Not everybody the same amount, but yeah. So it has, I don't know, I think it has the, what do you call them? I think it counts as a not easy course, and I would agree it's not easy. And the assignments are not, you don't want to leave them to the last minute because they do take a bit of time. But it does have the computer game aspect. It also has a very like strange. It's not a bell curve in terms of marks. It tends to be bimodal in the sense that there is a hump to I'm just passing, and there's a hump at I have almost 100 and out of 100, and that I think is because of the theorem prover, because you get immediate feedback if what you're doing is correct or not. And so if you're at the I'm just passing hump, you get some proofs going, but some proofs just not at all, and you basically fail at those proofs. But if you're in the normal bell curve area where you would be sort of in the middle, you would get pushed to the top, I think, because
Right.
the theorem
Right.
prover is going to tell you, you mistyped here. This is not quite correct, which is something you would get fewer marks if you in a pen and paper course, but which you can just go and correct. But
And you wouldn't even know that it's not correct.
exactly, yeah. And but that is, I think, an effect that will cost some people more time. So that is part of why you don't want to leave the assignments towards the end, because if you make those
Right.
mistakes, if you don't make them, it just like ideally an assignment you can type in probably 1.5 hours if you just know what the proofs are and you just type them in. But of course, that's never how it works. You find out what it is, and the number of mistakes you make and how long it takes you to backtrack determines the time, and that's very real. That's how all proofs work. That's how our proofs work as well. Right? Yeah.
How do you see the future of software foundation, specifically with interactive theorem provers?
How do I see the future? Hard to see the future is Yoda would say. So I think it is already spreading a lot more in industry. So I was talking about Apple using formal verification. they have a news item somewhere on their website about that. I know Amazon AWS, they like have a huge formal verification group. They're the vacuum cleaner of talent right now. If you want to hire people in formal verification, very hard to do. On the other hand, if you're a student and you want to make a lot of money and you're good in formal verification, or if you think you like formal verification, do that. It can be extremely lucrative. There's at least one student, from a student of mine, a PhD student, who works there now. She makes probably twice as much money as I do. And yeah, just, after one postdoc and so on. I mean, she's also very good. But, I've had that experience actually many times. It was a student who started with Google. He's not doing formal verification. He's more doing site reliability and so on. But
Mm-hmm.
he also just on his first day, twice the professor salary I had. So yeah. But yeah, that's good stuff. I mean, it's nice to see your students go there. Even sometimes you think, oh, maybe I'm doing the wrong thing. Maybe I should go there. But so I see that increasing. There's always a hype cycle, but I think we're mostly in the AI hype cycle right now and not in the formal methods hype cycle. It's for more critical things, I can see it increasing. I don't see people using formal verification for, I don't know, things like computer games or websites a lot, even though for websites and critical infrastructure, maybe people should. What I would hope is that especially infrastructure over time sees more of it and sees more of it applied. So one of the things we're doing with seL4 is we have this piece of software. And I mean, the first verification project finished in 2009, and now it's 2023, and we've maintained and extended the verification since then continuously. Like it's never not been verified, basically, since then. And I mean, by now, the size of the proof has increased dramatically. Like back then, it was about 200,000 lines, I think. Now it's like a good deal over 1 million. And yeah, I mean, that's just more, more features, more architectures, more properties, more stuff. Everybody wants more. People never want less. Like the best commits are, removing a few thousand lines from the proof because, you proved it a little bit nicer or you don't need it anymore or something. So that's, I think, how I see it going. More of it. For some areas, I think it is now cost effective. In the sense that it is better for your bottom line to do formal verification than not. Like it's going to be cheaper than doing testing to the same amount of assurance, at least, and it's going to be cheaper than failing. So I mean, I don't know what Apple discusses internally, but I think that's probably what they're realizing. Like they're applying it to sort of critical parts of their stack. I don't know exactly where, and it's but if that wasn't worth it, I don't think a company like Apple would be doing it. And similarly, well, AWS is a more not sure what I should call the approach. It's a broader approach, I would say. Like they're doing many different kinds of formal methods, and some are extremely successful. It's probably kind of a portfolio approach where you try many things and some are extremely successful and pay off and pay for all the rest, basically. Sort of, I don't know, VC startup kind of thing, maybe. That's how VCs see startups. You do 10 of them and one has a 10-time return and the others fail. So then you're still fine, right? Get two with a 10 times return and you're pretty good. Yeah.
So, what about tools? What sort of tools would you like to see going into the future developed for, formal methods to grow more?
Tools is hard. I want many tools. I don't. So it's dangerous to focus too much on tools, I think, in the sense that we're all people who like to build things and like shiny tools that make life easier, but
Yeah.
I don't think tools is what made our project successful as such. I mean, there were like without a theorem prover, of course, it would not have happened, and we built a lot of tools which made our life much better. But I don't think it was driven by the tools. So from that perspective, there's a whole bunch of things I want, but I don't know if it will make the fundamental difference as such. Like for Isabelle, for instance, I would want, I don't know. I don't actually know what I want. Usually more automation. Automation is good. And if you think of all the AI hype, give me a recommender system that would say, people who saw this proof state have done this thing before, and it has worked for them. Everything I've seen so far for that for proofs has been pretty bad. Like GitHub Copilot, for instance, works reasonably well for, I don't know, Java and maybe some Python and so on. I tried it on Isabelle, it was kind of catastrophically bad. But it also doesn't see the relevant information. It doesn't see the proof state, for instance. It just sees the rest of the proof text that you write. And like when I do a proof, the only thing I look at is the proof state. So, you know, there's a bunch of people out there who are building systems that are trying to take that into account. So maybe we'll see something there. But I think it has some potential, and I think that would be a better application of AI than many others. Like I would feel a lot better about that, for instance, than AI trying to write my code. Because if you write a wrong proof, the prover will tell you, hey, the proof is wrong, it doesn't work. If you write wrong code, you just have wrong code and you're going to run it and it's going to break. And it looks right and it will run in, it's like the worst case for formal verification. Code that looks right and works most of the time, but it's completely broken in many ways. I don't see good things coming there. But then again, job security. Hey, I should be happy about this. But maybe, I don't know. I'm not. So there's that in the Isabelle direction. In more general in verification tools, I think static analysis has more to give. Lower false positive rate, I think would be great. Like in other projects, like I have an open source project, JFlex, that I come back to every once in a while. I use a lot of static analysis tools on that, and there's still way too much noise, I think, there for Java. Even tools like Infer, they're good, but there's more that could be done, I think. And yeah, I'm not the person to do it, but I'm looking forward to the improvements in the field. SMT could be a part of the whole static analysis thing, where static analysis becomes more semantically interesting and deeper, basically. And I would see it more there than in actually doing more automated verification in terms of functional correctness. But I might be wrong. I don't know. The whole SMT automation thing feeding into tools like Isabelle, I can see that would be cool. More of that, and I think that is happening. There's many research projects around that. Yeah, that kind of stuff. Program synthesis is interesting. There's a whole bunch of work in proof engineering, proof repair, and so on. I
Right.
think there is a bit of, how should I say? I think the AI angle on proof repair is probably a bit over, how should I phrase it? Over optimistic, but there are more things that you can do in proof repair than AI, where it's more structural and sort of deeper and so on. Like Talia's work, for instance, I think is pretty cool. And sure, AI can help in sort of the heuristic side. I just don't think it's the magic bullet for all of these things. Like it seems to have trouble with anything that has a lot of structure and sort of deep logical content. It's better at, write me a poem about how AI is not good at facts. It's pretty good at that. But yeah. Yeah.
Well, I think I'm out of questions. I covered everything that I wanted to talk with you. Is there anything else you would like to talk about that we didn't?
I don't think so. I think we covered a whole lot of stuff. It's been fun. It was really cool. I haven't talked about that much formal method stuff for 2 hours in a row for a long time.
Yeah, I think that's the thing. Like, that's the reason I made the podcast, is that we don't get both to talk about this for that long and both to listen as well. Just sit down, like, and have something to listen, and the things that we love, right? So yeah, I hope people can get some enjoyment out of this as well. I think one thing that I wanted to ask is that, are you looking for hiring people for Proofcraft, or because I could leave some links for you, or things like that?
So that is an interesting question. We don't know yet. It
Okay.
depends on how it develops. So we're not how should I say? We're not the fast growing startup that wants
Hmm.
exponential growth and so on. We're kind of, and we're a services company anyway, and we don't take VC money, and we want to grow slowly and be sustainable, and mostly have fun doing what we're doing, kind of thing. So we are very careful with hiring. We will be applying for some big projects this year, and if they come through, then yes, there might be something, but it's a bit early to, um, say yes or no on that.
Awesome. Well, I think that was it then. Thank you so much for joining us, Gerwin. This was a lovely conversation. It was really nice to talk with you.
Yeah, thank you for inviting me, and yeah, it was really cool. Thanks.
Well, that was it for today's episode. I hope you guys enjoyed it as much as I did recording. Gerwin was such a nice guest. This work they've been doing with seL4 is just amazing. It's mind-blowing to me that people can actually do things so big with formal verification. It's a lot of work. If you guys have any questions about this, leave them as a comment in our website, typetheoryforall.com. You also can send us an email, typetheoryforall@gmail.com. And if you are enjoying this show so far, please consider contributing something in our Ko-Fi platform. You can find the links in our website in the bottom left. It's very hard to miss it. And I would greatly appreciate any contribution. Come on, $5, a coffee. Also, don't forget to follow us on Twitter. I've been posting some more memes now, quality memes in type theory and related stuff. So you wanna check that out. In any case, I hope to see you guys next time.